The weak law of large numbers tells us that the sample mean, that is, the average of independent identically distributed random variables xi, converges in a certain sense to a number, namely the expected value of the random variables xi. But it does not tell us much about the details of the distribution of the sample mean. The central limit theorem provides us exactly with this kind of detail. It tells us that the sum of many independent identically distributed random variables has approximately a normal distribution. The mean and variance of this normal is easy to find if we know the mean and variance of the original random variables. This enables us to carry out approximate calculations rather quickly by using the normal tables. We will start with a precise statement of the central limit theorem, and we will emphasize that it is a universal result. It holds no matter what the distribution of the original random variables, and for this reason it is very useful. We will work through several examples of the typical ways that the central limit theorem is used. We will develop a refinement that can be used when we are dealing with discrete distributions, which provides us with even more accurate approximations. And finally, we will revisit the polling problem and inquire again about the number of samples that are needed to obtain a certain accuracy with a certain confidence. We will see that the central limit theorem is much more informative, much less conservative, compared to the conclusions that we had gotten before based on the Chebyshev inequality. In this segment, we will first discuss and compare different views of the sum of independent identically distributed random variables, and then we will conclude with the statement of the central limit theorem. So let x1 up to xn be independent identically distributed random variables that have a certain finite mean and finite variance that we denote by mu and sigma squared. In order to have a concrete example in our hands, let us assume that this random variable has a distribution, let's say a PDF, that ranges from -1 to +1 and has a mean of 0. Let us look at the sum of these random variables. The sum has a variance of n times sigma squared, which goes to infinity, and correspondingly, the standard deviation of this random variable also grows to infinity. This random variable takes values between -n and +n, and because the variance and the standard deviation increase, this means that for larger and larger n, the width of this distribution is going to be larger and larger. We can obtain a different view of this sum if we divide it by n, in which case we obtain the sample mean. In this case, the variance goes to 0 as n goes to infinity, and as a consequence, the distribution is highly concentrated around 0. This is also what the weak law of large numbers tells us. The bulk of the distribution is concentrated in an arbitrarily small interval around 0, so this width becomes smaller and smaller as n goes to infinity. So in this case, we obtain a limiting distribution, but this limiting distribution is trivial, it's degenerate, it's all concentrated on a single point. How can we make it so that we obtain a limiting distribution that is more interesting? The key is to divide not by n, but to divide by the square root of n. This has the following effect. The variance of this ratio is calculated as follows. We take the variance of the numerator, which is n times sigma squared, and then we divide by the square of this number, which is n, and therefore the variance is equal to sigma squared. What's important here is that the variance stays constant. No matter what n is, the width of this distribution is going to be more or less the same. The distribution itself might change as n changes, but the distribution, at least in this case where we assumed 0 mean, the distribution stays in place, it doesn't move to the right or to the left, and its width stays the same. So one can wonder, in the limit as n goes to infinity, Does this shape start to approach a certain limiting shape? And if it does, what is the limiting shape that it approaches? The central limit theorem will give us the answers to these questions. The setting for the central limit theorem will be pretty much the setting that we were just discussing. So we will be looking into the case where we divide the sum of the random variables by square root of n, except for a few additional twists. Since this ratio has a variance of sigma squared, it would help to divide by a further factor of sigma here, so that the variance is going to become 1. And there's another issue. If the mean of the x's is non-zero, then the distribution is centered at a quantity that keeps changing with n. So the distribution will be drifting away from 0. It's not staying in place, and so it wouldn't have any hope of converging to something. For this reason, instead of looking at this ratio in particular, what we do is we first subtract the mean of the sum, which is n times the mean, and then we divide by a further factor of sigma. This random variable that we obtain here has nice properties. The mean of this random variable is equal to 0 because we did subtract the mean of the x's, and the variance of this random variable is going to be equal to 1. The reason is that the variance is the variance of the numerator, which is n times sigma squared, divided by the square of the denominator, which is also n times sigma squared. So as n changes, the distribution of the random variable Zn stays in place. It has a mean of 0, and its width more or less stays the same because we have a constant variance. We will compare this random variable with a standard normal random variable that has 0 mean and unit variance. The central limit theorem states the amazing fact that as n goes to infinity, the distribution of this random variable converges to the standard normal distribution in the following sense, that this probability here converges to that probability for any choice of little z. Now what we have here is just the CDF of this random variable Zn. So it tells us that the CDF of the random variable Zn converges to the CDF of a standard normal. And fortunately for the standard normal, the CDF is available in tables. So if we need to calculate the numerical value here, we can just look up the normal tables. And this suggests an approximation to this probability for the case where n is finite but large. When n is large, we can approximate this probability by this probability on the right, which we can find from the normal tables. The central limit theorem is a very important result. For this reason, we will spend some time discussing how to interpret it, what it means, how we use it, and we will go through a few examples to see how we actually apply it. The central limit theorem is absolutely remarkable. It is a very deep result and highly non-trivial and non-intuitive. There's no apparent reason why this random variable here, a standardized version of the sum of random variables, should have an approximately normal distribution. Furthermore, it is very useful, and one key reason is that it is universal. It doesn't matter what the distribution of the x's is. No matter what the distribution is, still in the limit, this standardized version of the sum is going to behave like a normal random variable. And if we wish to apply it to particular examples or models, the only thing that we need to know about the distribution of the x's are the corresponding means and variances, as we're going to see in multiple examples. When we apply it, it turns out to be very accurate. And it is also a very nice computational shortcut. Even if we knew in detail the distribution of the x's, in order to calculate the distribution of Sn, we would have to take the distribution of the x's and convolve it with itself n times, something that can be computationally tedious, whereas the computations that are involved when we use the central limit theorem are very, very simple, as the examples that will be coming up will show to us. Finally, at a philosophical level, the central limit theorem justifies why models involving normal random variables are very natural. Whenever you have a phenomenon or an object that's affected by multiple noise sources, and if these noise sources are independent, then the overall effect of those noise sources is going to be well modeled by a normal random variable, even if the distribution of each one of these noise sources is very different from being normal. And this is a reason why in many applications, in many different fields, normal random variables provide very useful and accurate models. Since the central limit theorem is so useful and important, it is worth making sure that we understand exactly what it says and to make a few comments on its mathematical content. What it says is the following. We take the sum of independent identically distributed random variables, we form this standardized version of the sum, where we subtract the mean and divide by the standard deviation of the sum, and then what it tells us is that the CDF of this random variable Zn converges to the normal CDF. So what we have is a statement about CDFs. It does not yet tell us anything specific about PDFs or PMFs. So for example, if Sn and the x's are all continuous random variables, so Zn is also continuous, you might wonder whether the PDF of Zn converges to a normal PDF. It turns out that there are results of this kind that assert convergence of the PDF or even PMF of this random variable to a normal PDF in some sense, but these results generally need a few more mathematical assumptions for the results to be valid. Nevertheless, when we show pictures of various examples, we will do this by showing pictures of PDFs and PMFs because these are easier to visualize. Now, since the result is so general and so important, it might be worth understanding to what extent it can be generalized to other contexts. Our main two assumptions are that the random variables are independent and identically distributed. Can we remove those assumptions? There are versions of the central limit theorem that apply to the case where the xi's are not identically distributed. One just needs to make certain assumptions on the means and the variances of the xi's. Some conditions will be needed. Also, the assumption of independence does not need to be literally true. There are versions of the central limit theorem that are valid when we have just weak dependence. That is, nearby x's may be dependent, but if you compare x5 with x of 1 million, then these two random variables are essentially independent. In those cases, we can still apply a suitable version of the central limit theorem. And finally, you may be curious how this result is proved. One way of proving it, which is the way it was originally established a long time ago for the special case of Bernoulli random variables x, in which case S is binomial, the way it was established was by carrying out algebraic manipulations on the binomial formulas. But this was a derivation that would not generalize. For the general case, the proof is obtained using so-called transform methods, which is a topic that we are not covering, but it goes as follows. We consider this function of the random variable Zn, where S is some parameter, and we show that this expectation converges to the corresponding expectation if you have the standard normal Z in the place of Zn. And that this is true for all S, or at least for all S in some rich enough set. And then one appeals to some deep mathematical results that tell you that if this kind of expectation converges to that expectation, then the CDF of Zn must also converge to the CDF of Z. But this is a proof that involves various steps and appeals to some deep results from other fields of mathematics. And finally, there is the practical side. What exactly does it say and how do we use it? Since the CDF of Zn can be approximated by the CDF of a standard normal, this means that in practice we can treat the random variable Zn just as if it were a standard normal. But now we notice that Sn is obtained as a linear function of Zn. Namely, the definition of Zn gives us this formula. So Sn is a linear function of Zn. If we pretend that Zn is normal, and since linear functions of normal random variables are normal, this means that we will also pretend that Sn is normal. So in practice, the way to carry out calculations is often to just pretend that Sn is normal with the appropriate mean and variance. These are the correct means and variance of Sn, and that's the only information that we need in order to apply it. If we know mu and sigma squared, and using the normal approximation, then we have an approximate distribution for Sn, and we can go ahead. Now, in practice, can we use the central limit theorem when n is moderate? For example, if n is 30. Can you apply the central limit theorem? This is a relation that's true in the limit of very large n. How large should n be? It turns out that the central limit theorem gives us very good approximations even when n has moderately small values. Now, these approximations sometimes will be better and sometimes worse. It helps if the distribution of the x's that you're starting with has some common features with the normal distribution. If the x's are already normal, then S will be normal and there's no approximation involved. If the x's are close to normal, then for fairly small values of n, S will be very well modeled by a normal random variable. Now, what does it mean that the distribution of the x's looks a little bit like the normal one? It helps if the distribution is symmetric around its mean, and it also helps if it is unimodal in the sense that it has a single peak rather than multiple peaks. Let us now look at some numerical examples to get a feel for how the central limit theorem works in practice. Let us look at a discrete random variable that has a uniform distribution in the range here from 1 to 8. If we add two independent random variables drawn from this PMF, we obtain a random variable whose PMF is the convolution of this PMF with itself. We can even carry out this calculation by hand and we get a triangular PMF. So this is what we get for the case where n is equal to 2. Now we can keep doing this. If we add 4 of these discrete uniforms, of course assumed independent, then we obtain a PMF that starts to have a shape close to that of a normal shape. And if you take as many as 32 of them, then the PMF of the sum of 32 discrete uniforms is almost identical to the shape that you would get if you were to draw a normal PDF. So with n as small as 32, we have essentially converged. In fact, this convergence is so good that in practice, quite often people use this idea to generate random samples of a normal random variable. What do? You draw 32 random samples from a discrete uniform, add them up, and what you get is a sample of essentially a normal random variable. Now, in this example, things worked out well for us because the distribution that we started from was nicely symmetric and didn't have any strange features. Things are not always so favorable. Let us consider starting from a truncated geometric. If we add 8 random variables that are independent and drawn from this distribution, what we obtain is a PMF of this form, which does not really look like a normal shape. The reason is that there is a pronounced asymmetry. So let us add more and more independent x's. If we add 16 of them, we start to get something that's a little closer to normal, but the asymmetry is still visible. And if we add 32 of them, we can still see some asymmetry, namely this tail here does not look exactly like this tail out there. So in this instance, it's really the asymmetry of the original distribution that makes it difficult to converge, and it will take larger values of n before we can get a very accurate approximation. We will now go through a sequence of examples that illustrate the different types of questions that we usually answer using a normal approximation based on the central limit theorem. In general, one uses these approximations to make statements of this type: that the probability of the sum of n IID random variables being less than a certain number, that this probability is approximately equal to some other number. Notice that this statement involves three parameters, a, b, and n, and you can imagine problems where you are given two of these parameters and you're asked to find the third. And this gives us the different variations of the questions that we might be able to answer. So we will go through examples of each one of these variations. Our setting will be as follows. We have a container, and the container receives packages. Each package has a random weight, which is an independent random variable that's drawn from an exponential distribution with a parameter 1/2. And we load the container with 100 packages. We would like to calculate the probability that the total weight of the 100 packages exceeds 210. For example, 210 might be the capacity of the container. Since we will be using the central limit theorem, we will have to work with the standardized version of Sn, in which we subtract the mean of Sn and divide by the standard deviation of Sn. And to do that, we will need to know the mean and the standard deviation. Now for an exponential, the mean is the inverse of lambda, and the standard deviation is also the inverse of lambda, and so we know what these quantities are. Then the next step is to take this event here and rewrite it in a way that involves this random variable. So what we do is that we take the original description of the event, subtract from both sides of this inequality this number n times mu. In this case, n is 100, mu is 2, so we subtract 200. Divide by this quantity, square root of 100 is 10 times sigma, this gives us 20. And we do the same on the other side of the inequality. This is just an equivalent representation of the original event. But what we have here is the probability that this standardized version of Sn is larger than or equal to this number, which is 0.5. And at this point, we can use the central limit theorem approximation to say that this probability is approximately the same if we use a standard normal instead of Zn. Now for a standard normal, we can calculate probabilities in terms of the CDF that's given in a table, but here we have the probability that Z is larger than something, not smaller than something. The CDF gives us the probability that Z is less than something. This is easy to handle. This probability is 1 minus the probability that Z is less than 0.5, which is 1 minus the CDF of the standard normal evaluated at 0.5. And at this point, we look up the normal table, the standard normal table, and for a value for an argument of 0.5,
the corresponding value is this one. So we obtain 1 minus 0.6915, which evaluates to 0.3085, and this is the answer to this particular problem. In the next example, we ask a somewhat different question. We fix again the number of packages to be 100, but we're given some probabilistic tolerance. We allow the packages, their total weight, to exceed the capacity of the container, but we don't want that to happen too often. We want to have only 5% probability of exceeding that capacity. How should we choose the capacity of the container if we want to have this kind of a specification? So we proceed as follows. We want this number 0.05 to be approximately equal to this probability, but now we take this event and rewrite it in terms of the standardized random variable. That is, we start from both sides of the inequality and subtract n times mu, which is 200, and then divide by the standard deviation of Sn, which is this quantity, and which is 20, exactly as in the previous example. And now this random variable Zn is approximately a standard normal, so we're asking for the probability that the standard normal is larger than or equal to something, which, using the argument as in the previous example, is 1 minus the CDF of the standard normal evaluated at this particular value. Now, what this tells us is that this quantity here, the value of the CDF, should be equal to 1 minus 0.05. So this quantity here should be 0.95. What does this tell us about the argument of the CDF? We can look at the table and try to find somewhere an entry of 0.95. And we find it either here or there. We could choose either one, or we might decide to split the difference and say that we get a value of 0.95 when the argument is 1.645. And so we conclude that in order for this to be 0.95, we need a minus 200 divided by 20 to be equal to 1.645. And then we solve for a, and we find that a should be 232.9. And we can choose the capacity of our container this way. Our next example is a little more challenging. Here we will fix a and b, and we will ask for the value of n. Here's the type of question that has this flavor. We're given the capacity of our container. We want to have small probability of exceeding that capacity. How many packages should you try to load? What is the value of n for which this relation will be true? So we proceed as usual by taking this event and rewriting it in a way that involves the standardized version of Sn. So we need to subtract n times mu, which in this problem is 2 times n. We subtract it from both sides of the inequality, and then we divide by the square root of n times sigma, which is 2. So we divide both sides of the inequality by this number. Once more, this event here is identical to the original event, but now it is expressed in terms of the standardized version of Sn. This is a random variable that's approximately a standard normal. So once more, we're talking about the probability that a standard normal exceeds a certain value, and by the central limit theorem, this is approximately equal to 1 minus the standard normal CDF evaluated at this particular value here. Now we want this quantity to be approximately equal to 0.05, which once more means that this quantity should be 0.95, and arguing as before that we try to find 0.95 in the standard normal table, and this tells us that the argument of the normal CDF should be equal to 1.645. Here we get an equation for n. Unfortunately, it is a quadratic equation. However, we can solve it. And after you solve it numerically or using a formula for the solution of quadratic equations, you find a value of n that's somewhere between 89 and 90. Now, n is an integer, so you could choose either 89 or 90. If you want to be conservative, then you would set n to the smaller value of the two and set n to be 89. Our last example is going to be a little different. Here's what happens. We start loading the container, and the container has a capacity of 210. Once we load the package and we see that the weight has exceeded 210, we stop. Let capital N be the number of packages that have been loaded, and this number is random. If you're unlucky and you happen to get lots of heavy packages, then you will stop earlier. We would like to calculate, approximately, the probability that the number of packages that have been loaded is larger than 100. Now, this problem feels a little different. The reason is that n is not the sum of independent random variables, and so we do not have a version of the central limit theorem that we could apply to n. What can we do? Well, we try to take this event and express it in terms of the xi's. And here's how we go about it. What does it mean that we loaded more than 100 packages? This means that at the time that we were loading the 100th package, we didn't stop, and this means that at that time, after we loaded the 100th package, the weight had not exceeded 210. So the event that we're dealing with here is the same as the event that the first 100 packages have a total weight which is less than or equal to 210. But now we're back into a problem that we know how to solve, and the way to solve it is to take this random variable, standardize it. This actually is essentially the same calculation as in our very first example, and we will get the standard normal CDF evaluated at 210 minus the mean of this random variable, which is 200, divided by the standard deviation of this random variable, which is 20. So we're looking at phi of 0.5, which we look up at the standard normal table and has a value of 0.6915. So this was our last example, and these four examples that we worked through cover pretty much all the types of problems that you might encounter. Of course, sometimes it might not be entirely obvious what kind of problem you are dealing with. You may have to do some translation from a problem statement to bring it in the form that we dealt with at this point. But once you bring it into a form where you can start to get close to applying the central limit theorem, then the steps are pretty much routine as long as you carry them out in a systematic and organized manner. An important application of the central limit theorem is in the approximate calculation of the binomial probabilities. Here is what is involved. We start with random variables xi that are independent and they have the same distribution. They're all Bernoulli with parameter p. We add n of those random variables and the resulting random variable Sn, we know that it has a binomial PMF with parameters n and p. We also know its mean and we do know its variance. What the central limit theorem tells us in this case, since we're dealing with the sum of independent identically distributed random variables, is the following. If we take this random variable here that we have been denoting by Zn, which is a standardized version of Sn, we subtract the mean of Sn and divide by the standard deviation, this random variable has a CDF that approaches, as n goes to infinity, the CDF of a standard normal. So let us use what we now know to calculate some probabilities. Let us fix some parameters. N is 36, P is 0.5, and we wish to calculate the probability that Sn is less than or equal to 21. Now, in this case, we can calculate it exactly using the binomial formula. The probability of being less than or equal to 21 is the sum of the probabilities of all the numbers from 0 to 21, and this is the probability of obtaining a number k. And by calculating this expression, we obtain this number, which is the exact answer. Now let us proceed using the central limit theorem. We are interested in this probability, but we will use the fact about the CDF of this related random variable. So the first step is to calculate n times p, which is 18. The second step is to calculate this denominator here, which in our case evaluates to 3. Now, since we know something about the CDF of this random variable, what we need to do is to take this event and rewrite it in terms of this random variable. So we have the event of interest, which is that Sn is less than or equal to 21. This is the same as the event that Sn minus 18 is less than or equal to 21 minus 18, and it's the same as this event here where we divide both sides by 3. Now what we have here is the probability that this random variable Zn is less than or equal to 1. But now Zn is approximately a standard normal, so we can use here the CDF of the standard normal distribution, which is phi of 1. And at this point we look at the tables for the normal distribution. We find this entry here, and this gives us an answer of 0.8413. This is a pretty good approximation of the exact answer, which is 0.8785, but it is not a great approximation. It is off by about 4 percentage points. Can we do better than that? It turns out that we can get a better approximation, and let us see how this can be done. Recall that we approximated this probability using the central limit theorem and found this numerical value. But we make an observation that this probability is equal to this probability here. Why is that? Sn is an integer random variable. Therefore, if I tell you that it is strictly less than 22, I'm also telling you that it is 21 or less. Therefore, this event here is the same as that event here, and therefore their probabilities are the same. So instead of using the central limit approximation to calculate this probability, let us follow the same procedure but trying to calculate this probability here. And this probability here is equal to the probability that Sn minus, we subtract the mean divided by the standard deviation of Sn, is strictly less than 22 minus 18 divided by 3, which is the probability that the random variable that we denote by Zn, which is this expression here, is strictly less than 22 minus 18 over 3. This is 1.33. Now at this point we pretend that Zn is a standard normal random variable. The probability that the standard normal is less than a certain number. This is the standard normal CDF evaluated at that number. And then we look up at the normal tables at 1.33 and we find this value of 0.9082. Now we compare this value with the exact answer for this problem, and we see that we again missed it. Using this approximation to this quantity gave us an underestimate of this number. Now we obtained an overestimate. The true value is somewhere in the middle. So this suggests that we may want to do something that combines these two alternative choices here. But before doing that, it's good to understand what exactly have we been doing all along. What we're doing is the following. We have the PMF of the binomial centered at 18, which is the mean. It's a discrete random variable. But when we use the central limit theorem, we pretend that the binomial is normal, but while we keep the same mean and variance. Now, when we calculate probabilities, if we want to find the discrete probability that Sn is less than or equal to 21, which is the sum of these probabilities, what we do is we look at the area under the normal PDF from 21 and below. In the alternative approach, when we use the central limit theorem to approximate the probability of this event, we go to 22 and we look at the event of falling below 22. This means that we're looking at the area from 22 and lower. So in one approach, this particular region is not used in the calculation. That's what we did here. But in the second approach, it was used in the calculation. Should it be used or not? It makes more sense to use only part of this solid region and assign it to the calculation of the probability of being at 21 or less. Namely, we can take the midpoint here, where the midpoint is at 21.5, and calculate the area under the normal PDF only going up to 21.5. What this amounts to is looking at this particular event here. Now this event is of course identical to these events that we have been considering, because again Sn is a discrete random variable that takes integer values. But when we approximate it by a normal, it does make a difference whether we write the event this way or that way. So here we're going to obtain the probability that the standardized version of Zn is less than, we follow the same calculation, but now we have 21.5 minus 18 divided by 3. And this number here is 1.17. And using the central limit theorem calculation, this is the CDF of the standard normal evaluated at 1.17, which we can go and look up in the normal table to find a value of 0.8790. And now we notice that this value is remarkably close to the true value. It is much better as an approximation than what we obtained using either this choice or that choice. And since this approximation is so good, we may consider even using it to approximate individual probabilities of the binomial PMF. Let's see what that takes. Let us try to approximate, as an example, the probability that Sn takes a value of exactly 19. So what we will do will be to write the event that Sn is equal to 19 as the event that Sn lies between 18.5 and 19.5. In terms of the picture that we were discussing before, what we are doing essentially is to take the area under the normal PDF that extends from 18.5 to 19.5 and declare that this area corresponds to the discrete event that our binomial random variable takes a value of 19. Similarly, if we wanted to calculate approximately the value of the probability that Sn takes a value of 21, we would consider the area under the normal PDF from 20.5 to 21.5. So let us now continue with this approach. We do the usual calculations, which is to express this event in terms of standardized values. That is, we subtract throughout the mean of Sn and divide by its standard deviation. So what we obtained here is the standardized version of Sn, and that has to be now less than or equal to 19.5 minus 18 divided by 3, which is the probability that our standardized random variable lies between 0.17 and 0.5. And now if we pretend that Zn is a standard normal random variable, which is what the central limit theorem suggests, this is going to be equal to the probability that a standard normal is less than or equal to 0.5 minus the probability that it is less than 0.17. And if we look up those entries in the normal tables, what we find is an answer of 6.915 minus this number, which evaluates to 0.124. And what is the exact answer if we were to use the binomial probability formulas? The exact answer is remarkably close to what we obtained in our approximation. This example illustrates a more general fact that this approach of calculating individual entries of the binomial PMF gives very accurate answers. And in fact, there are theoretical results to this effect that tell us that this way of approximating asymptotically as n goes to infinity and in a certain regime does give us very accurate approximations. We now revisit the polling problem that we have studied earlier. When we first looked at that problem, we used the Chebyshev inequality to obtain certain bounds and numerical results. What we want to do now is instead to use a central limit theorem type approximation, which we hope that it will be more accurate and more informative. Let us remind ourselves of the setting. We want to estimate a certain number p, which is the fraction of the population that will vote yes in a certain referendum. And we estimate p by picking a sample out of the population. We pick n people, we pick them randomly, uniformly over the population and independently, and for each one of the people in the sample, we ask them if they will vote yes or no, and we record their answers in Bernoulli random variables xi. So by the assumptions that we have made, these xi's are independent Bernoulli random variables, and their mean is equal to p. We count how many x's were equal to 1, that's the number of yeses, we divide by n, and that gives us the fraction in the population that have responded yes. This is the sample mean of the x's. And we use this sample mean to estimate the unknown fraction p. We would like the error in our estimation to be small, that is, the difference between the sample mean and the true value p to be small, less, let's say, than 1 percentage point. Now, there's no way of guaranteeing that this spec will be met with certainty unless we sample almost everyone in the population, but what we can do instead is to ask that these specifications are violated with only a small probability. So we look at the probability that our estimation error is larger than what we want. This is the case that we do not meet the specs, and we would like this probability to be small. And one possible question is what the value of n should be in order to meet these specs. But in order to do any calculations, we first need a way of approximating this probability. And we will do that using the central limit theorem. And the central limit theorem involves this standardized version of the random variable Sn, where Sn stands for the sum of the x's. We know that this random variable is approximately normal, and what we want to do now is to take this event and rewrite it in an equivalent way, but which involves this random variable Zn. So let us start. First we note that here we have a mu and a sigma, so we should know what these are. For a Bernoulli random variable, the mean is what we already wrote down, and sigma is the square root of p times 1 minus p. Now let's look at this event. Mn is the same as Sn divided by n by definition. And p, we can write p in this form, minus n times p divided by n. And we want this quantity to be larger than or equal to 0.01. So this event here is identical to that event up there. This starts to look like this expression. P is the same as mu, but there is a little bit of a difference in the denominator terms. So let's see what we can do. Let's take this same event, but multiply both sides of the inequality by square root of n. This causes this denominator term to become just square root of n, and we get a square root of n term in the numerator on the other side. This is an equivalent description of the event, and now we can multiply both sides of this inequality by sigma, actually the denominators of both sides by sigma, and we obtain this equivalent representation. But now we notice that here we do have the random variable Zn that we wanted, and so we managed to express this event in terms of the random variable Zn. In particular, what we have is that this probability is the same as the probability that the absolute value of Zn is larger than or equal to 0.01 square root of n divided by sigma. And then we can use the central limit theorem approximation to approximate this probability by the corresponding probability, where we now use a standard normal random variable instead of the Zn random variable. So here Z stands for a standard normal random variable with mean 0 and variance equal to 1. Let us now continue on a new slide so that we have some working space, and here is the result that we have derived so far. If somebody gives us the value of n, we would like to be able to calculate this probability using this approximation. However, there's a slight difficulty because sigma is a function that depends on p, and it is not known. However, as we discussed when we first studied the polling problem, we do know that sigma is always less than or equal to 1/2. And this suggests that we could use here the worst case value of the standard deviation, replace sigma by 1/2, and instead look at this probability here. How are these two probabilities related? Which direction does the inequality go? A sketch will be useful here. Z is a standard normal, and it's centered at 0. Somewhere here we have a value of 0.02 square root n, and somewhere further out we have the value of 0.01 square root n divided by sigma. Why are these two values ordered this way? Since sigma is less than 1/2, 1 over sigma is bigger than 2, so this expression here is bigger than this expression there. Since the inequality goes this way, Now we can compare these two events. This event, that z is larger in absolute value than this number, is the probability of this tail of the distribution, and we will have a similar probability from the other end of the tail of the distribution. Here we're talking about the probability of being larger than or equal to this number, which would correspond only to this part of the tail and similarly a small part of the tail from the other side. So the blue event is smaller than the red event. This is the probability of the blue event, so it's going to be no larger than the probability of the red event. So now, if somebody gives us a value of n, we should be able to calculate this probability. How do we calculate it? The probability that the absolute value is above a certain number is equal to the probability of this tail plus the probability of that tail. But because of the symmetry of the normal distribution, this is twice the probability of each one of the tails. Now, what is the probability of this tail? It's 1 minus the probability of whatever is below that. So it's 1 minus, and the probability of being below that, this is the standard normal CDF evaluated at 0.2 square root n. And so we do have now an expression for the desired probability, or at least a bound for it, which is expressed in terms of the standard normal CDF. If somebody gives you a value of n, you can plug in here. If n is 10,000, then square root of n is 100, and this number becomes equal to 2. And so in this case, what we obtain is that the probability of interest is less than or equal to 2 times 1 minus phi of 2. And now we invoke the standard normal table, and from the normal table we obtain that this quantity is equal to twice 1 minus 0.9772, which evaluates to 0.046. So, if we use 10,000 people in our sample, then we will get an accuracy of 1 percentage point with very high probability. The probability that we do not meet the specification, so that the accuracy that we get is worse than 1 percentage point, that probability is quite small. It's 0.046, that is 4 and something percent. This is pretty good. And suppose that your boss now tells you, I only want the probability of not meeting the specs to be 5%. You look at this result and you say, with 10,000, I achieved a probability of a large error that's less than 5%. This means that I probably have some leeway and that I can reduce the size of my sample. What could the size of the sample be and still meet those specs? What we're trying to do here is that we have this approximation for the probability of interest, and we want to set this probability to a value of 0.05. And then we want to ask what is the value of n that will result in this particular probability of not meeting the specs. Now we can do the algebra, and we find that this corresponds to requiring that phi of 0.02 square root n to be equal to 0.975. What's the interpretation of this? We want to choose n so that the probability of the two tails is 5%. This means that we want this probability here to be 2.5%. This means that the probability of whatever is to the left of this number should be 0.975, including the tail. This means, again, that we have to look at the standard normal table and ask what's the value for which the CDF is equal to 0.975. So we look around and we find 0.975 to be here, and it corresponds to 1.96. So this tells us that 0.02 square root n should be equal to 1.96. And then we solve for n, and we find that the value of n is 9604, which is indeed some reduction from the 10,000 that we had originally. So how does this relate to the real world? When you read newspapers about polls, you will never see sample sizes that are about 10,000. You will usually see sample sizes of the order of 1,000, sometimes even smaller. How can they do that? Well, they can do that because the specs that they impose are not as tight as the specs that we have here. Usually they tell you that the results are accurate within 3 percentage points, let's say, instead of 1 percentage point. And by moving from 0.01 to 0.03, and if you repeat those calculations, you will find that a sample size of about 1,000 will actually do.